The hydrocyclone, as we know, what is happening in the hydrocyclone is very complicated. There's a very complicated physical phenomena. For me, it was important, again, to look in the literature to try to find some promising mathematical models. I didn't develop on myself these models, to be honest. We centrifuge many equations. That was my development. Here, what we want regarding a design. So you see the hydrocyclone, we have a definite feed, a definite volume, flow rate, cubic meters per hour or liter per minute, liter per hour, a definite solid mass fraction in the feed, and a definite particle size distribution by mass. We have the overflow, that means due to the centrifugal force here, we have an overflow, volume flow rate here, solid mass fraction in the overflow, and here is the particle size distribution for the overflow. Similar. Volume flow rate in the underflow here, solid mass fraction, and here particle size distribution of the underflow. In many situations when we use filters, for example, drum filter, belt filter, when we have a relatively low solid mass fraction of the feed, we use a hydrocyclone to have a concentrated suspension, and this underflow will be the feed of the filter apparatus. That's why it's very important to be able, not only because of the belt filter or the drum filter, in many applications it is very important to be able, for example, to have in design, I want to have here a definite pressure drop, yeah? That is the potential here for the separation, a definite pressure drop, a definite volume flow rate, a definite cut size, that means the cut size of the hydrocyclone, and the definite underflow solid mass fraction. Tell me what diameter I need, how many hydrocyclones in parallel connection, and here what is the underflow diameter here, yeah, to achieve this solid mass fraction in the underflow. Another option is that the standard calculation or the performance calculation, you have the hydrocyclone, you have the number of hydrocyclones in parallel connection, you have the feed flow rate, and you have the underflow here diameter of the apex. And then you want to calculate what is the pressure drop, what is the cut size, and what is here the solid mass fraction. Okay? These are two approaches. Is the standard calculation having the apparatus, or the design, I want to know the diameter and the number. And you see a typical design here. Suspension characterized by viscosity, density of the filtrate, of the liquid, solid density, solid mass fraction, and particle size distribution by mass, accumulated. We want to have a definite volume flow rate. We want to have a definite pressure drop. We want to have a definite cut size and a definite solid mass fraction in the underflow. The question is that, what is the diameter of the cyclone? What is again the number of cyclones in parallel connection? What is the underflow diameter of the apex? What is, for example, the overflow, the solid mass fraction in the overflow? What is the total efficiency? That means mass of solids in the underflow over mass of solids in the feed. What is the particle size distribution in the overflow and in the underflow? Yeah? So, I don't want to go into equations here. Trust me that these are tested equations. What I want to say, we need, because of the complexity of the phenomena, a lot of adaptation parameters. Yeah? That means totally here 1, 2, 3, 4, 5, 6, and another one that is here the standard deviation, I will explain you that totally we need 7 adaptations parameters. How I get these 7 adaptations parameters now? Better I show you the software so that we can, you have an idea how we proceed here. Solving a design or a standard calculation problem. That is a software that will be finished, deliverable in 2 months. Yeah, we do some. So you see, we have a suspension database where we can enter all suspension, needed suspension data for any simulation of a hydrocyclone. And there is a distinction here, is one group suspension characterizing parameters like viscosity, densities of liquid and solids, solids mass fraction, that is here black are calculated parameters, only blue are inputs, and here is the mean for the particle size distribution, and here is the standard deviation. You can see the particle size distribution also here. That means you can enter, you measure the particle size distribution, you enter here your X and F, and automatically the program calculates your XG and sigma G. That means the mean and the standard deviation. Yeah? So, and you can save any suspension here. It's another suspension. That is another suspension. Okay? That is the suspension database. You have also Cyclone database. Here you can enter the geometrical data of any hydrocyclone of any manufacturer. You can see here is a filter based on manufacturer, and here you see the name of the cyclone series. The cyclones, different diameters, belong to the same family or to the same series if approximately the relative parameters are the same. Yeah? And this is assuming that cyclones with the same, to the same family, that means the same specific parameters here. Sorry. Yeah? The same specific parameters, like here, you see, length, total length of the diameter of the cyclone over the diameter, cylindrical diameter, and so on. Angle here, that is the angle of hydrocyclone. These are the relative parameters, approximately the same, not depending again on the diameter. You see here the different cyclones of the same family. And here, that is the name of the cyclone series. That is the inlet type. It can be circular or rectangular. And here, that is the feed option. It can be involute, outer wall, tangential, that is the default case, and so on. So we have here again, and as last, the minimal and maximal pressure depending on the diameter of the cyclone. So again, here, that is the cyclone database. And as I told you, if we have a definite design task, I told you, you see here the 7 adaptation parameters, 3 experiments are enough for achieving, for getting reliable values of all these 7 adaptation parameters. Just a minute. You see here, these are the 3 tests with the smallest hydrocyclone of the given series, yeah, to determine the 7 adaptation parameters, because only when we have these adaptation parameters, we are able to do a simulation of the performance of the hydrocyclone for any settings, yeah? And you see here, we have one hydrocyclone, the smallest of this series, yeah, that is this hydrocyclone here, this one, 50 millimeters. And then we measure, we have 5%, that is the fit for all 3 tests the same. And then one test with 2 cubic meters per hour, the second test with 4 cubic meters per hour, the settings, and the other with 6 cubic meters per hour. The underflow diameter 12, 10, 8 millimeters, apex. The underflow flow rate, these are things that we have to measure. The underflow flow rate, and that is the solids mass fraction in the overflow for the 3 tests, and that is the pressure drop we also have to measure. With this data, we get as a result, as you see, these 7 adaptations parameters, alpha, beta, gamma, alpha 1, beta 1, gamma 1, and that is here the sigma S. What is the sigma S? The sigma S is actually when we proceed with simulation and we have the fit curves here. Is them better in this case? I use this. The sigma S is how the grade efficiency curve can be described by 2 parameters, the x50, the cut size, and the spread of this curve characterized the geometric standard deviation, which is characterized by the sigma S. You see that? That means the sigma S is important also for the determination of, for the design. Again, the first is we have to guarantee that our suspension is entering the database. We have to guarantee that our cyclones family are entering the database. Then we go and analyze the 3 tests and we determine these parameters. And these parameters, that is what we see here with black. That means these are the determined adaptation parameters, and you see another 3. These 3 are constant. That means are the same. We don't have to determine this. After many investigations, these 3 parameters can be considered constant. Only these 7 parameters we need, and then we go to the simulation. So a simulation and this simulation, that means a design simulation, consists of 2. Design. You see, I have this material data and I want to do a design, 1 bar pressure drop, 100 cubic meters per hour feed flow rate, 30% solids mass fraction in the underflow, and a cut size of 20 millimeters. That is for me the requirements for the design, so that I have again 100 feet and 30 mass fraction percent, and that is the QU. 8.9 cubic meters per hour will go to the bell filter. Yeah, that is the underflow flow rate. Okay? As you can see, it's very user-friendly because the program calculates left and right the possible values, mean and maximal possible values, and the result is here. We need a diameter, that is the theoretical design, the first design step, 73 millimeters, and 12.89 number of cyclones in parallel connection, yeah? And then we go to the second design step, that is this one, where based on that, I have to show you that, apply results to the standard, and you see now we are in the standard in the second design step, where we take this data, that is the 100 and the 30%, and then of course we have to take a diameter from the database. We just click here, we choose that, okay, and now we have 75 millimeters, and we say 12. The number cannot be integer, is an integer number, and that is all. That means we have now our design, and we are able to see also the feed curves. You see here, that means the particle size distribution in the overflow. That is the feed, and that is the particle size distribution in the underflow. We can have the grade efficiencies here. Reduce grade efficiency of for this design, and we can check, we can study also the influence of any parameter on the results, on the hydrocyclone performance. You see all the parameters you can select as y-axis x-axis parameter, iteration parameter. And you can see here also linear or logarithmic. So, sorry, you can see here, and you can see also the program distinguish between influencing parameters. That means here the pressure difference is the iteration parameter from 0.35 to 4. And here you see all these parameters are influenced by delta P. And these parameters are constant, are not influenced. So automatically you can know every parameter you select as iteration, which parameters are influenced, result parameters are influenced by this iteration parameter, and which remain constant. So you have a high flexibility regarding, you can again study the influence of any parameter. If I can conclude, design option, we have here the possibility, and here is a summary what simulations we have, what analysis test we have. Here again, you have a database for suspension, including the particle size distribution. Here, you have the cyclones database, and it's very easy for doing a simulation just here. Plus, what is your project? What is your material? What is your cyclone? Name of the simulation, and then okay, you have immediately a simulation result. Yeah? So that is very easy to have to simulate the performance, but again, to simulate the performance, you need adaptation parameters, and we need the test, the experiments, and I showed you that these 7 adaptations parameters, we can have them only from 3 experiments. If I reduce, imagine I have only one experiment. In this case, we cannot have reliable data for only one experiment. We need at least 3 experiments for having that. And as you can see, we have some curves here which shows us about this accuracy, because we see we have also fit of this here. That is again important to have a test, to have at least 3 tests with the smallest cyclone of the given series. And having these adaptation parameters which I showed you, that is very user-friendly to get these parameters. And again, these are the inputs. So that means from each test, we have to measure or set in definite parameters, which I explained to you. And then we can have a design or a standard calculation of a hydrocyclone. Thanks for your attention and your questions.
Thank you very much.